Chapter 2, Exercise 20. Hints. Assume that the closure of a connected set E is not connected and derive a contradiction. Interiors of connected sets are not necessarily connected. As a counterexample, consider the subset of the Euclidean space R2 defined by E equaling this. The set E consists of two open half-planes and the point here. Solution. First, we prove that the closure of a connected set E is connected. Let E be a connected subset of X. Suppose that E bar is not connected. Then there exists non-empty separated sets A and B such that E bar equals this. Since E is non-empty, we have E equaling this. One of the sets, here or here, must be non-empty. Without loss of generality, assume this. Since this and that, the sets this and this are separated. Indeed, since this, Theorem 227c implies that this and similarly that. Now this and analogously this, showing that E intersection A and E intersection B are separated. As E is connected, one of these sets must be empty. Thus this, which implies E subset of A, since this. It follows that E bar is subset of A bar by Theorem 227c. Consequently, B equals this, contradicting the assumption that B is non-empty. This contradiction proves that E bar is connected. Next, we show that the interiors of connected sets are not necessarily connected. Before constructing a counterexample, we prove an auxiliary result. If set E alpha is a collection of connected subsets of a metric space X, and this, then that, is connected. To see this, fix a point P element of this, and assume that this is not connected. Then there exist separated non-empty sets A and B such that this. Without loss of generality, assume P element of A. For every alpha, we have this. Since E alpha is connected, this and that are separated, and this. It follows from definition 245 that this for all alpha. Thus, B equals this, contradicting the assumption that B is non-empty. Hence, this is connected. Now, consider three subsets of R2, E positive, E negative, and set containing 0. Define E equals this. We will show that E is connected, but its interior, E suc, is not. For any P in this, consider segment IP, which joins 0 to P. This segment is connected. See remark to exercise 21. Moreover, for P in E positive, we have this and that for t equals 0. Similarly, for P in E negative, we obtain this. Thus, this. Since the IPs are connected and share a common point, our auxiliary result implies that E is connected. Next, we determine E suc. For any P, this, the neighborhood this is contained in E positive, proving that E positive is open. Similarly, E negative is open. Thus, this. Since in each neighborhood of set containing 0, there is a point on a real axis, we have that this. Finally, from this, it follows that E suc equals E positive union E negative. However, since E positive and E negative are disjoint and open, they are separated. By example 19b, E suc is not connected. Here is a picture. The set E equaling this is connected because its every point is connected to 0 by a segment in E. Comments. Theorem 247 characterizes all connected subsets of the real line. The only connected subsets of R are this, where A be element of R and A less than or equal to B. In Euclidean spaces of dimension greater than 1, there exist many more connected subsets, often with complex structures. In solving this exercise, we prove that the union of any collection of connected sets with a non-empty intersection is connected. This implies that in any metric space X, for each point P in X, there exists the largest connected set containing P. This set is called the connected component of X. Different connected components are closed and mutually separated, forming a partition of X. Thanks for watching.